All right, let's dive in. We're talking about a field that really does feel like a kind of modern-day alchemy, machine learning. But instead of trying to turn lead into gold, we're transforming raw data into predictions, into insights, and even into brand new creations. So, how does this digital alchemy actually work? Let's break it all down.
I know, it sounds a little bit like science fiction, doesn't it? But really, this is a central question that machine learning, or ML, is trying to answer. It's all about giving software the ability to learn and act without us having to explicitly program every single step of the way.
Now, the absolute heart of this entire process is something we call a model. Just think of it as the brain of the whole operation. We feed this brain just massive amounts of data, and through all that training, it learns to spot patterns, predict outcomes, or even, create something completely new.
And this right here, this highlights a huge shift in how we solve problems. You see, the old way of predicting the weather involved trying to perfectly model all the laws of physics, which is, an incredibly complex task. The ML approach is completely different. Instead of teaching it the rules, we just show it the results, tons and tons of weather data, and we let the model discover all the hidden patterns for itself.
So, how do we even start teaching these models? Well, the most common way is with our first major category, supervised learning. I want you to think of the model as a student who's being carefully guided by a teacher who already knows all the answers.
The concept here is actually beautifully simple. We give the model a massive data set where all the answers are already labeled. It's almost exactly like giving a student a giant stack of old exams with the answer key. They study the questions, they see the correct answers, and they start to intuitively understand the patterns that connect them.
Now, within the supervised learning, we can basically ask our model to do two main things. The first is what we call regression, where we want it to predict a specific number, like the future price of a house. The second is classification, where we're asking it to choose a category. Is this email spam or not spam?
And we can get even more specific with this. Classification can be binary, a simple yes or no, like rain or no rain. Or it can be multi-class, where there are a whole bunch of possible outcomes to choose from, like predicting if it's going to rain or hail or snow or sleet.
Okay, but what happens when we don't have that answer key? Well, that brings us to our next two schools of thought, where the model kind of has to figure things out on its own. Welcome to the world of unsupervised learning. Imagine just dropping a model into this giant sea of unlabeled data points. There are no guides, no right answers, it's just a chaotic mess of information. And the model's job? To somehow find the hidden structure.
And it does that using a really cool technique called clustering. The model looks at all that raw data and just starts to find points that are similar to each other, and it groups them together into these distinct clusters. It's kind of like finding constellations in a massive field of stars.
And this is the absolute crucial difference. With classification, remember, we tell the model what to look for. We define spam. But with clustering, the model finds the groups entirely on its own. It's then up to us, the humans, to look at those groups and say, aha, that cluster over there represents our summer weather patterns.
All right, now for our third type, reinforcement learning. This is all about learning from trial and error. So, an agent, think of a robot or a game-playing AI, it takes an action. It then gets feedback, a reward for a good move, a penalty for a bad one. It learns from that feedback, and over millions and millions of attempts, it develops a policy, which is just a fancy word for its winning strategy. This is exactly how we train an AI to master a game or teach a robot how to walk.
And that brings us to the grand finale, the branch of ML that is truly, it's architecting our reality, generative AI.
So, unlike the other models that are mostly predicting or classifying things, generative models, they create. They learn the underlying patterns of massive data sets so incredibly well that they can produce brand new content that fits those patterns perfectly. We're talking stunning images, evocative poetry, and even functional software, all created from scratch.
Just look at this incredible versatility. We can give it text and get back an image. We can give it an image and get back a detailed description. We can even combine inputs, like an image and a text prompt, to get a newly edited image. It's like a true digital polymath, able to work across all these different media to create something totally new.
And this creativity isn't just limited to the arts. Take a look at this, a text-to-code model. You can ask it, just in plain English, hey, write me a Python loop to find prime numbers. And it generates this. This elegant, functional piece of code, this is what we mean when we say clean code poetry. And this highlights something absolutely crucial. For these models to be truly useful, especially in technical fields, every single detail matters. Getting the syntax right, like is underscore prime equals false with the underscore, that's not just a minor point, it's everything. In the world of code, precision is absolute power.
So, after all of this, the question really isn't just about what these tools can do, but what you are going to do with them. When you think about your next project, do you need the predictive power of regression for system alerts? Or do you need the creative force of generative systems to handle automation? The choice and the power is yours.